Our project is about using breath and saliva analysis to test for cardiovascular diseases, and our mentor is Dr. Jack Wong, which he specialized in vascular regeneration and metabolism, I think. Yeah. So, a brief introduction on cardiovascular diseases first. Okay, so each year 17 million people die from cardiovascular disease, so it's a severe disease, and 86% of these premature deaths, which is deaths caused by cardiovascular disease before the age of 70, which is about the average life length of a human being nowadays, is usually from low and middle income countries or developing countries. So the normal way of testing for cardiovascular diseases would be you have to go to a hospital and a healthcare profession sticks a needle in your vein to extract some blood in order to test for B cell, T cell, or other volatile organic compounds, which has caused a great problem because you have to go to a hospital, and because it's an invasive method, so you can't really do it at home. So this research caught my attention a few weeks ago, which is actually nothing related to cardiovascular disease. It may sound completely irrelevant, but it's a research done by CUHK, Professor Lo Yongming 教授, which is a screening for Down syndrome in the fetus before the baby was born, basically. So the traditional method, and when I say traditional, it's about 20 years ago, let's say, it's a doctor will have to stick a needle into the mother's womb in order to extract amniotic fluid to test for DNA samples and protein plasma in the amniotic fluid to test for these genetic diseases. And about 10, 15, 20 years ago, Dr. Lo developed a method which is you can basically obtain about, just wait, I've got it noted down somewhere, 3.4% to 6.2% of the DNA samples found in the bloodstream in the mother is actually from the fetus. So you can take these DNA samples or RNA samples and do an analysis based on these samples. So you don't have to stick a needle into the womb in order to get the amniotic fluids, which may harm the baby. So that's the basic theory, finding a non-invasive or relatively non-invasive method to test for disease. And also it takes a shorter period of time for the analysis. It's about 3 hours for the whole test, and you can get the results like in a day. So this research introduced us to two main things. Number one is it's finding a suitable biomarker to test for, which may be a protein or a volatile organic compound. And the other one is to find a non-invasive method. So going back to cardiovascular disease, you can see there are a bunch of volatile organic compounds which you can test for as a bioindicator for cardiovascular diseases, which includes oxygen-containing compounds like acetone, methanol, ethanol, and hydrocarbon compounds like ethane or isoprene, etc. And there are also some other which is less used, like no, I think ammonia is actually quite often used, which is a nitrogen-containing compound. These compounds can be found in saliva and exhaled breath. So then you can just collect our exhaled breath and do the analysis based on these samples. The common method is by using gas chromatography and mass spectrophotometer or something. I can't remember what it's called. So yeah, so this is what we've been talking about, a non-invasive way. The next slide. Yeah, so here are a bunch of the bioindicators, the chemicals. And there's a certain range of these chemicals, which is like the normal range. For example, if you're testing for nitric oxide in the blood, it would be 10 to 50 ppb, sorry, part per billion, my bad. So it's a very low concentration. So if it's slightly elevated, let's say 150, which may indicate that there's something wrong with your metabolism. And it could be because of a heart failure, an aneurysm, a deep vein thrombosis, etc. So again, there are different testing methods for it, and we have found that if we're going to test for exhaled breath, which is a gas sample, it's not a liquid sample, and most of these tested samples are volatile, then most of the studies we've been doing usually use GCMS to do it. So yeah, I think we can skip this one. So here are a few biomarkers that have already been proven which can be used in testing exhaled breath to identify cardiovascular diseases. So there's isoprene and TMA. TMA is an amine compound, which I think comes from a gut bacteria, and this bacteria emits this amine compound, which will cause plaques and blood clots to basically dislocate and go into the bloodstream, which may cause a stroke. So it's cardiovascular disease. And alkanes, N-alkanes, so basically carbon compounds with compounds with 4 carbon to 20 carbons can be tested for a grade 3 heart rejection, which is after you've had a heart transplant and your body system rejects the transplanted heart, but it's not a very common disease, so the implications are quite limited. And another one that caught our attention is a less used bioindicator, which is a C-reactive protein. It is very commonly used in other testing subjects, like testing blood samples and sometimes saliva. But in exhaled breath, we haven't been able to find a lot of research that implements C-reactive protein as a bioindicator, but we have done a bit of research and found that actually there is a certain amount of a short chain protein plasma which can be found in exhaled breath, and one of the most common one is the C-reactive protein. So a summary of all the biomarkers, we've decided that these 4 biomarkers would be a good start to do our research.
Okay, so this we kind of we kind of need a short introduction before we skip to this part, because we did not mention what this is. So can you skip a few slides down? Yeah, there should be a yeah, this one. So since we're analyzing VOCs, the volatile organic compounds, we have to inject it into this whole machine. This is the gas chromatography, which is just like normal chromatography, but it's for gas. So in like science lessons, we have like those paper strips which show that, for example, dye A would go to, like, for example, a certain length and distance, and dye B will go another. And gas chromatography, it's kind of similar. So after the gas goes through the column, it goes through the mass spectrometer, and then it comes out as also a piece of paper that shows like the gases in like mass to M2Z ratio, but then it's basically the other way of showing the distance that the dye went. Yeah, correct. So we're talking about the GC column that was like spiraling. So this is how we choose a different GC column for like different gases we're trying to analyze. For one, the film thickness. So you can see there's thin columns with thin film and thick film. So for us, we're focusing more on the thick film part because, as you can see, applications, the first point, volatile. Since, like, for my part, I'm basically researching on isoprene, and isoprene is a highly volatile gas, and so we need the thick film for this. Yeah, you can see that there's a longer retention time, and then it has a lower maximum temperature, because, well, if it's too high, you lose the gas, right? Okay, next one. Okay, inner diameter for the GC columns. So for most of the research I found on like isoprene and VOCs, we're using mostly like 0.32 and also 0.53 IDs, which is just for the, well, I'm not really sure why we use those, but then we do. So as you can see, applications like splitlets, like headspace, on-column injections, these are mainly because, so basically you inject the gas into the tubes. You imagine columns as a tube, and on-column is basically injecting. For example, headspace is basically zipping the whole container and then letting the VOCs accumulate in the headspace above the liquid, or so then you can take it away from the container, like by only using the needle to extract the headspace, so they call it. There's also something called it's fine. There's also something called a liquid-liquid extraction, which is basically you mixing the VOCs with liquid, but it doesn't work for any VOCs that will, well, melt in the liquid and mix with them. So you cannot choose polar VOCs that will be miscible in aqueous solutions. You can only use some that, for example, like hexane. So you will evaporate the liquid later and then just extract it. So length. We usually use, the most commonly used is like 30 meters because it's just like the middle. It will be suitable for like most VOCs, and especially for our isoprene research, it's using 30 meters because, so they use shorter columns to prevent like on-column decomposition, such as baseline distortions or like very asymmetrical peak shapes in the further MS results. So we use 30. Okay. Thank you. We are going back to this. Limitations. But before I go to limitations, let me just say what we found for isoprene. So from studies we've come across, GCMS for isoprenes and nitrates were usually performed with RTX 200 columns, which is just like a type of column, that's a name. And then it's fine. 30 meters long, like 0.32 mm ID I just mentioned, with 1 of stationary phase thickness. And it's, because can we go back to the last slide? Thank you so much. So as you can see, there's a gas tank there. That is not the sample. That is the carrier gas. So you're supposed to have another gas, inert gas, that carries the sample through, like that's the injection part. And then this is just the inert gas that carries through the column. So for the isoprenes, they usually use helium. Because, yeah. And then another thing that varies across like GC columns is the catalyst. Like some GC columns are catalyst coated. It's a widely investigated area because it kind of enhances the performance by increasing the oxygen vacancies and also spillover effects. So what they are is basically increases the electron transfer speed, and also it helps like form a double layer on the catalytic films, so the reactants don't bind onto like the column walls. And well, if it binds, then it'll slow down, and also you lose some of the components you're trying to test in the way. Yep, and Thank you. Limitations of Excel breath analysis. So you can see these, but also because, as we said in the front, no, thank you. Isoprene has like about 105 parts per billion, which is already a lot compared to other gases. But then, even though it's one of the most, where's my paragraph? Okay, anyways, you can still, it's not easy to detect it still, because they have, the current technology is not that advanced in the detection of any sub ppb level of components, so like it's not accurate, and it's like selectively detectable sometimes. So yeah, that's one of the limitations. And okay, another is that GCMS is a highly volatile, reliant, machine. So if the component is not volatile, you will not be able to test it, or it'll be even more not accurate. That's why it's hard to use breath, or because, for example, C-reactive protein, which mentioned previously, it's more in the saliva, so it's not as volatile as isoprene. So that's why they don't use GCMS for C-reactive protein. And also for mixture, you'll only be able to differentiate some of the gases, and it's, as Eva said, they're too low in concentration. And also, because volatility also links to heat, so this requires high heat. So as our goal was to make it a portable machine. It's kind of hard because, you can't carry something that's 350 Celsius in your hand, can you? Yeah, that's why we need more investigations to make it fully portable. Maybe heat insulating for 350, which is kind of crazy. Can we go back to the previous slide? Okay, so just some procedures on how to calibrate this machine before you work it is to set the injector and also detector temperatures. It won't be too high because the columns each have a maximum temperature you should not exceed. And then you purge your column at ambient temperature with the inert gas only. So that's the only thing that goes through the columns, and you kind of cleanse it a bit for at least 15 minutes. Then you load your method to appropriate flow rates, which you don't the gas doesn't go whoo, it goes at the certain flow rate you're set it to be. Then you condition the columns at the suitable temperatures for your components, your test analytes. And then you test it with some other gas which you know the components of, which and then you'll get a MS result that, you expect to see. Then everything's set. Then you inject the sample you're trying to do. Yep, so that's kind of how you calibrate this GC column and how you use it. That's the end. Thank you.